Okay, so when we talk about waves, we know that a wave is a disturbance which propagates through a medium with little or no net displacement from the particles of the medium. So here's an example, of a water wave. And if you notice the medium here, right, is the water, the wave is going through, and the water is moving a little bit, but not a whole lot, right? The wave, though, is moving from left to right. Here's a little pulse wave, right, moving across. And then a people wave, right? So, one gets to the next, gets to the next, to the next, the next, and so on, right? And then the wave goes by. And so the parts of the wave are going to be important to remember. We know that the wavelength is from a crest to a crest or a trough to a trough. So in this case, the length of that would be 4 meters. And then the amplitude is from equilibrium to a crest or equilibrium to a trough. What it's not is from a trough to a crest, and that's a common mistake. The amplitude is just from the equilibrium to a crest or equilibrium to a trough. So a wave is the motion of a disturbance, right? So if you disturb or vibrate a surface or an object, a wave is going to go through it. And so the medium itself is that physical environment, whether it's water or even a rope or whatever. And so any wave that requires a medium is called a mechanical wave. And so that's going to be our focus in this section. The speed of a wave itself is given by, you can just take distance over time. How far does it cover in a certain period of time? Another way to look at that is, and this is new, we take the wavelength and multiply that by the frequency, and that will give us how fast it's going as well. So we'll look at an example of that. We know the frequency of a wave is how many cycles per second that we have. And so the period of a wave is the time for a full complete cycle to go by. And they're inversely related to each other. Remember, frequency is 1 over the period. So how many cycles, right? How many cycles in a period of time? You take the period of the wave divided 1 divided by that. That'll give you the frequency. Therefore, the period is 1 over the frequency, and both are important to use some, depending on what you need them for. Okay, so let's go ahead and try this sample problem here. Ocean wave passes by you as you float in the water. The time between crests are 10 seconds, and the distance between the crests are 20 meters. And go ahead and figure out the speed of the wave. I say velocity there, but really without direction, it's the speed. So go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. Okay, so 20 meters is the wavelength. The time is 10 seconds, and therefore the frequency is 1 over the period, so 0.1 hertz, and therefore the speed of the wave is 2 meters per second. You could have also used speed equals distance over time as well, right? And that would give you, how far or how fast it goes, 20 meters in 10 seconds. So as we look at different kinds of waves, if we have a slinky, and let's say we place the slinky on a surface and we had some tape here, and we sent a wave through the slinky, well, that tape and the slinky itself is going to be going back and forth, right? So it's just back and forth. Now, we can contrast that to a rope, let's say. Let's say we had a rope here, and let's say we send a wave through it, and, it's like this, right? And the wave's going through. That medium, right, is moving up and down. So as it goes from left to right, the medium moves up and down itself. And that's different than this kind of wave right here. And so those are the two basic categories. The transverse wave is where the particles move in a direction perpendicular to the motion. So in other words, if we had a rope and that rope is, as the wave goes by, the medium itself is moving up and down, whereas the wave is going from left to right. They're perpendicular to each other. And so waves on a string would be a good example of that. Longitudinal waves are where the particles move parallel to the direction of the wave motion. And these are also called compression waves. And that is actually what we just did with the slinky. The slinky, is moving back and forth as the wave goes there. So the movement of the particles is parallel to that motion. So sound is an example of that. Yeah, here's a good visual of a transverse wave where the movement of the particle is up and down, the energy is going from left to right, or the wave is going from left to right. Longitudinal wave, the movement is back and forth with the energy going from left to right, or the wave going from left to right there. So again, another visual to continue forward here. When we look at a reflection of waves, this is where a wave hits a boundary and bounces back to the original, or bounces back into the original medium itself. And it's reflected, and as long as there's no friction or thermal energy generated, the energy will stay the same there. So here's an example of a wave that hits a fixed end. The fixed end is not free to move. The wave hits it and then actually inverts. It goes in an inverted phase. It's completely out of phase as it bounces back. And so the reason this happens is due to Newton's third law, right? The wave hits the wall upwards, so the equal and opposite reaction is the downward reflection of the wave. Now the open end is where this is free to move. So this, as the wave hits, the wave can come up to here, and it sends back the same way because it's really just kind of redirecting the energy of that wave. Okay, so when we talk about different kinds of waves, we can talk about a pulse wave, which is just one singular wave coming by. I think I showed you a clip of that at the beginning. And so, when you have the source of a wave motion that is periodic, meaning that it's continual, and so like, moving your hand in water continually, that's a periodic wave where you keep sending those waves. A sine wave is created where you have something in simple harmonic motion. And when we looked at those graphs, the sine graphs, being sine and cosine graphs being produced there with that motion, that's because, as it moves back and forth, we have those amplitudes, we have the time that it takes to go back and forth, and that actually creates those sine waves there. And so, as we consider the different kinds of waves, they're going to fall into those different kinds of categories there.